meeting is being recorded. So my name is Rima Musa, and I'm the Cybersecurity Awareness Coordinator here at UC Santa Barbara. And as you may know, it's National Cybersecurity Awareness Month throughout the month of October, and the importance of cybersecurity in daily life is perhaps greater than ever. Technology alone can't always protect our computers and information, so being aware of information security issues and following best practices are excellent ways to protect yourself, your family, and the UC community as a whole. And attending sessions like these is a great way to increase your awareness and help yourself and your community to be cyber safe. So given the current COVID-19 pandemic and life online conditions we've been privy to for the past few months, all of our programming this month is entirely virtual and system-wide across the UC system. So we have events from many of our different campuses across the UC system that you are totally free to attend. So if you'd like to check out some of the other great webinars and virtual programming that we have going on this month, please click this link that is about to be sent out through the chat. Second. And here it is. And you can peruse through that website. It has all of our events for the rest of the month, and you can register for any or all of the events and add to your calendar once you register through Zoom. So for this session, we'll be hearing from Dr. Chad Spensky, founder and CEO of Allthenticate and a former gaucho. So we'll be hearing from him in just a bit on binary exploitation, but first off, I'd like to briefly introduce him, and I'll do that as he gets his screen sharing all set up. And then we'll hear from him and save the last 15 or so minutes for Q&A. So you can share your questions now or throughout the session through the Q&A button that you should see at the bottom of your screen. And yeah, we will try to get through as many questions as we can before we wrap up at 1 o'clock. So a little bit about Dr. Chad Spensky. Chad is a computer security researcher, entrepreneur, and educator who is passionate about using technology to make people's lives easier and their digital systems more secure. Chad has more than 10 years of research experience and is a lifetime hacker. Formerly, he was a member of the technical research staff at the MIT Lincoln Laboratory and has since continued to help them solve some of the Department of Defense's toughest cybersecurity problems. He received his PhD from UCSB in 2020, and he possesses a master's in computer security from the University of North Carolina at Chapel Hill, as well as a BS in mathematics, a BS in computer science, and a minor in economics from the University of Pittsburgh. So I'm going to give Chad a moment to share his screen, and we'll figure out what's going on with his video. But in the meantime, feel free to get started, Chad.
Gotcha. So you can hear me, right?
Yep, we can hear you.
All right. It says that the host has my video stopped. So I will, I guess, be mysterious, which is suitable for this talk until we get the video on.
Yep.
So the title of this talk is Binary Exploitation, How to Be an Elite Hacker. And kind of the intent of this is, I think, in general, hackers are quite mysterious. You hear that someone got hacked and no one really understands what that means. You know, what do you mean you got hacked? There's so many different definitions of hacked. So the goal of this talk is going to be first to define hacking. What is it that we mean by hacking? Then what is a binary? If we're given a talk about binary hacking, it seems like that's probably important. What is exploitation? That's also kind of an important topic. You know, what does it mean for a company or a service to get exploited? And what does any of this have to do with security? Like, what am I even talking about? And what is the implications of this on my life? And then finally, I like to, follow up all these talks with, can we do better? What does the future have in store for us? And are we doing anything better for the future? So let's start with the first obvious question. What is hacking? If you would look this up in the dictionary, it would give you a pretty weird definition: to cut or sever repeated, irregular, unskillful blows. That's probably not what this talk is about today, at least, I hope not. If you look at definition 4, to gain illegal access to a computer system or network, again, maybe, but I haven't broken many laws in my life, and I consider myself a hacker and do a lot of hacking every day. So that can't be the correct definition. Maybe it's the intransitive verb, to write computer programs for enjoyment. I do that. So if I'm a hacker, that does seem to fit the bill. And to gain access to computer illegally. Again, most hacking is not illegal. It's actually really fun and just exploratory. So I feel like this, even defining hacking, I don't even like the definitions I find online. I kind of like this one a little better. If you can hack it, is to be successful. So I'm hoping that there's actually a correlation there, that because I can actually hack it, that means I'm gonna be successful in my life. So I like this definition the best. But we go to Hollywood, they try and show people what hacking is on screen. It either looks like this guy on the left, who I think just really likes glare on his monitors. I've never seen anyone intentionally face lights at their monitor. Or the guy on the right that I don't know how you work like that, but I do like the Starbucks cup in this totally bizarre world. Again, my office doesn't look like this, nor does many hackers I've met in my life. So the whole external persona of hacking, I think, is completely wrong and just scares people, because it sounds so elite and it must take the smartest people on earth to do this, which it doesn't, unfortunately, but it's very fun. So who are these people, right? Are they Neo from the Matrix? Are they, you always think of like these nerds doing weird stuff in their basement. This guy in the middle has like a Nintendo controller on his arm. I don't know, maybe I would probably wear that thing. I'm not sure what it does, but that's not what hackers look like. Or they're this mysterious guy shroud in the shadows down here in the corner. So the definition, I think, of hacking and who hackers are is they're just normal people trying to answer one critical question: how the heck does this thing work? Pick whatever you want for that thing. It could be a computer, it could be a car, it could be a refrigerator, and really just digging in to how it works at the fundamental level. And they actually call it getting owned when you get hacked, because in a sense, the hacker owns the thing more than you own it. So for me to take over your computer, I actually have to have a better permission on that computer. I have more control over your computer than you have on it. So even though you physically own it and paid for it, I sort of technically own it because I have more power over it. So in my mind, just trying to figure out how things work. And when you figure out how they work better than the people who built them, you can hack them. So for the portion of this talk, let's figure out how the heck computer programs work, right? We want to do binary exploitation. We want to hack computer programs. Fundamentally, how these work. So step one, we're going to write human readable code. We need some way to input this program into a computer, and humans have to read and write that. From there, we're going to take that human readable code and we're going to do what's called compiling it, and compile it into machine readable binary code. So this is where the phrase binary exploitation comes from, and binaries in general, if you've ever heard that. And then we're going to feed this machine code into the computer. And then finally, profit, right? The computer runs and we have all these beautiful things that we have today, and iPhones and all these great interfaces all do these fundamental 4 steps. So first, we'll do some human readable code. We'll start with pseudocode. So there's no, the computer will never understand this code, but we want to, outline what we want the program to do. So this one has 3 steps. We're going to get the password from the user. So we need to display some prompt. It says, hey, enter your password. If the password's correct, we proceed. Otherwise, we abort, right? A simple program to just check a password and do something, maybe just print something on screen. So then we're going to write this in computer code. So this immediately looks way different. And you can see the things with the / in front of them are comments that I put in the code. So again, it's pretty human readable. The names all kind of make sense. Don't worry about any of the special characters. But I didn't want to give an elite hacking talk and never use C. So here's some real low-level code of how you'd interact with a computer. So we have a buffer that stores secret. The user is going to input 20 characters. So we're going to say input password. So you'll see this little prompt. You type whatever you want, hit enter, and then we compare. If the input equals the password, they win. If it doesn't, they lose. So we now take this and convert it to machine readable code. This is actually the exact same program written in x84 assembly, x86 64-bit assembly. I can speak today. And you can see now this even gets a little more detached from what a human can read, but you can still kind of make it out, right? You have this move, RCX, keyword pointer, and then we even add some comments here. So you know that that's the word secret, this is input password, here's some print things, but we don't really write in assembly these days. We're far beyond that. We have nice programming languages. And then the final step, we get our binary. So we compile it. And this is what it looks like. Ta-da, right? This is literally a computer program. This will execute. This is the exact function I just showed you. You wrap some other stuff around this, feed it into any modern day processor, it'll run it. And this is what it looks like when I randomly smash the keyboard with my fingers. So there's not much difference there, right? It's just kind of random stuff. So this is kind of the hard part, right? So what ships as a computer program is this, which is pretty much the same as this when you show it to a human. So now I'll sort of walk you through what we're looking at. So first, to understand a binary, you need to understand that it's just a different base. It's just a different way of counting. So over on the left is what you're used to. The numbers 1, 2, 10, 16, 256, 1024 mean exactly what you'd think they'd mean. If I have 10 dogs in the room, there will be, you can count them. There's as many as I have fingers on my hand, right? So then we move over to base 16. So this is what you were seeing when I showed you the compiled code. It was written in base 16. So 1 is 1, 2 is 2, 10 is A, 16 is now 10 because your base, you add a 0 every time you hit a new base. 256 is now 100, 1024 is now 400. And then we look in the final column, we have base 2. So in base 2, you only have ones and zeros. So if you hear about hackers talking about, oh, it's all ones and zeros, that's actually true. 1 is actually on. You could think of turning a light switch on. 0 is off, so turning the circuit off. But you can count with that, right? So 1 is 1, 10, 1, 0, and then it keeps incrementing. To make this a little more readable, and so it's less confusing, we add prefixes to these numbers. So base 16 gets a 0x for hexadecimal for 16. Binary gets a 0b for binary. So now when you see these numbers, you immediately know that even if it's a 1 in base 16, or it's a 10 in base 16, and you can reason about them. This is sort of just a nice lesson so you understand what I mean by binary, is that we compile this down to just ones and zeros, and that's why we call it a binary. So we know how computers work. Now when you know, we know how programs work. Now we know how a computer works, right? Because what we want to hack is the program running on the computer, and that's what we're going to exploit. Fundamentally, we have really 3 components. We have the hard drive. So this stores everything persistently. You can save something on your hard drive, power it off, power it on, it'll still be there. The CPU, or central processing unit, this is the brain. So this actually does the computation. And then we have the memory, which will store things temporarily. So when the program's running, it will be in memory. Any interactions will be in memory. And the reason for this is that memory is about 100 times faster than the hard drive. So this is how computers have gotten so quick. You do the slow thing on the hard drive to store it long term. And when you're actively working on something, it's in memory. And then you throw the computer program in here. So put the computer program on the hard drive, it then loads it to memory, and then goes into the CPU. So every time you run a program, it's on the hard drive, loaded into memory, CPU runs it a little bit at a time. So if we look at that program in memory, like I said, step 1 is going to be take this from the hard drive and load it into memory. We have really 3 sections that we'll create in memory. And there's some really cool stuff that goes on under the hood, where to every program, they see they think they have exactly a brand new stick of memory with nothing else on it, and it's all abstracted away. So the program actually thinks this is all that exists, even though there's thousands of other programs running. At the bottom, you have your code segment. So this is where all the program data goes. So this is actually the code that's going to execute. Then you have the heap. So this is any sort of long-running things in the program, but it's program data, right? So it's, you want to store something, the person inputs their username, and you want to keep the username for the duration of their login. You store that on the heap. And the stack is any temporary data, just stuff that you need to while you're computing. So think of me giving you a math problem, and you need to just write some stuff down to figure out the answer. And the second you figure out the answer, you throw that sheet of paper away. That's what the stack is for. Hey, I need to figure this out. The computer needs to save some data just while it computes this thing, and then it's done, throw it away, right? So we're not keeping it long term, literally just scratch paper, but in a digital form. So if we look at the program running in memory, we're just going to look at the stack in the program. So I'll snap back real quick just for the color coding. So the bottom is the code, the top is the stack. And if we write this out in pseudocode, we'll look at the program, it'll say do something. I'll save this for later, where this just says hi there. We do something else, and then later in the program, we say, oh, I wanted to read this again, right? So we know, oh, we put that on the stack, that was our scratch paper. Give me that thing back, I'm gonna do something with it, right? So it's a pretty simple concept. You just have the program data and some place that you can store your work as you're working on it. One of them's code, one of them's data. They're on the same memory stick. So now it becomes a little more interesting because you can say, do something, save this for later, do something else, and then execute this other thing. So you can actually put data that will point to code. So if you ever heard the word pointers, this is what that means. But now you're saying, I'm putting something there, but I need to execute it as well. So give me that thing, that's an address to some more code. So you can see here that the stack is going to point back to the program data. So what this looks like, we look at our little program from earlier. Remember, it just stores two things. It's going to have the secret, the input, and then it checks them. So if we look at this in data, there's going to be your input that the user is going to put in. So I reserved 3 memory chunks, or just addresses in memory. There's 64 bits wide. So for us to store 20 characters, you need 1 byte per character. So we have 3 of those. That's our 24 bytes. Sorry, I didn't shift this up. I actually moved the stack around a little bit last minute to make this make more sense. But there you have 24 bytes there for your input, and then your password is there, and your return address is all stored on the stack. And what the return address does, if you can see it in the program, once it checks the password, it's going to have to go back somewhere, right? So it's got to go do something else. And this is telling it, execute this next, right? You did this thing, you checked the password, and whether it checked out or didn't, I need to know where in the code to keep executing. So at this point, if we were in person, it'd be very nice to poll the audience and say, do you see a problem? So you there in front, yes, I see the same problem you see, is that you can actually overwrite the important stuff in there, right? The password was overwritable, and this return address where you tell it to execute is overwritable. And the reason that is that it's all stored in the same place. And for those of you who are familiar with gets, it's a very unsafe function. So the problem here that is exploitable is that gets doesn't check the length. You can give it as much data as you want, and it'll just keep reading it in. So what ends up happening is that you have your user input, 24 bytes filled up, but I gave it way more than 24 bytes. So now where the password was stored is also filled up with whatever I put there, and the return address where it's going to execute code also is whatever I put there. So here's where the first idea, which is called smashing the stack for fun and profit, the first paper that came out, said, hey, what if I put that return address to point back at the stuff I just put in there, right? So instead of telling you the password, I'm going to write a snippet of code that says, do whatever I want it to do, and I'm going to put my own new password, and then I'm just going to point back to my code. So it doesn't even matter if you check the password, because the second that you return to anything, boom, you're going to where I want you to go. And it's my code I just gave you. So this is effectively an exploit in my mind. This is a binary exploit. This is what the elite hackers are doing, right? You're actually doing memory corruption and rewriting the machine in a way that's not supposed to work that way. So we've owned this machine, right? This program written by the programmer is never supposed to run code that, let's say, turns on your speaker and says hello. But we can do that now with this program because we're writing our own code in memory. So what can go wrong? No problems here. Actually, you can do anything you want. This is called, arbitrary code execution. You could read files, you could write files, you could talk to other computers on the network, you can record the camera and microphone, literally let your imagination run wild. It's bad, right? So this was kind of the early day of computers. This is how things worked. Once exploits got out of control, hackers got really skilled. We needed to do something about it. We can't just let people keep smashing our stacks and running whatever code they want. So one of the first ideas that came about, which I really like, it's very elegant and novel and simple, was that we put a canary on the stack. And the reason I call it a canary is because in the coal mines, I actually grew up in West Virginia, so this one kind of hits close to home. You would never know if there was enough oxygen to breathe. So they would take a canary down there, and apparently canaries would die much sooner than humans. So you carry the canary, and if the canary dies, it's time to get the heck out of that coal mine because there's a gas leak or something that killed the canary, and off you go. So what we do here is on the stack now, we put all of our normal stuff, but then in between the return address, we put a random value that cannot be read by the hacker. And then they check if the canary does not equal the canary value, panic and stop executing because they could get code execution. One of the other cool things, I guess sort of simple ideas, was that you make sure that the data segments cannot be executed, right? This kind of makes sense in hindsight, like why would you ever run why would you ever run data as code? But initially, we're just impressed that computers even worked. So now pretty much every computer on Earth with a stack in the heap which store the data, right? Your scratch paper can no longer run code, and then it makes it a little harder on the attacker. So anytime they try to execute code from there, it just says no, program crashes, no one gets hurt. But hackers are smart, right? There's no way they just stopped there because, I'm sure you read the news this week and there's probably another exploit, right? And some of these cool binary exploits still happen. So the way that they do this these days, which is really clever and really fun to do, so if you're interested in this, I'd recommend trying to write your own attack. It's called ReturnOriented Program. And the idea here is that on the return address, right, in the program, we could point it to wherever we wanted to. So what we do is we point it back in the code, where we point it to in the code, we'll do just one very simple little thing, and then go back to look at the stack to say, what should I do next? And then we say, I'll go do this other simple little thing. And it says, okay, I did it. What do I do next? So you can chain all of these together like puzzle pieces. So you're only corrupting data, but the data is telling it where to execute. And you're using code that's already on the computer, which it's a very large program. There's a lot of code. Think like Microsoft Word, that thing's huge, right? You can find all these little gadgets that they call. And then you can just keep pointing it to the little pieces at a time. So do this one, then do that one. And before you know it, you wrote an entire program using code that's already on the computer itself. And I've heard hacking as described as programming a weird machine, which I think is a great definition. So when you're just writing a computer program, you play by the normal rules of computer programming. If you're a hacker and you're hacking a program, you play by these new rules, and every program is going to give you a new rule. Every system is going to give you a new rule. And you just have to adapt and program that machine now. You don't get to play by normal rules. You play by different rules, but it's a game you can still win. So what makes this really complicated, and sort of why I think this is shrouded in so much mystery, is that we went forward in this example, right? We wrote the pseudocode, we saw the C code, and then we kind of just worked our way through how things could go wrong. But what happens in the real world is that hackers have to go backwards. So you're going to give me a binary that, might as well look like the matrix, right? It's just zeros and ones. And what I have to do is use tools to take that binary and turn it back into the machine code. So this is called assembly code. There's tools to do this. This is actually using Ghidra, which is an open source reverse engineering tool that was made by the NSA, actually. So taking that binary, I can reverse engineer it, and you see and hear stuff like I showed you earlier with the assembly code. And then we want to take it a step farther, and we'd like to see source code. So Ghidra can actually do what's called decompilation, and it will take the binary and try to pull out source code that kind of makes sense. So this clearly is not the source code that we wrote earlier with all of my beautiful comments, but it starts to look a little bit more human readable. And then from here, as a hacker, you have to then dig through and look for something that went wrong and poke around here and say, wow, this calls fget, that seems vulnerable. But that's really the process. It's nothing like in the movies. It's not this like, oh my God, we're frantically hacking, doing all this amazing stuff. You sit and stare at this for hours to days to weeks to years, right? Until it's like, ah, I found something that the programmer screwed up and now I can take advantage of it. So what we learned today, hopefully, I went a little bit quickly, but I'm hoping that the Q&A will be cool, and I have a live demo I wanted to get to kind of show you what this looks like. So we learned how computers execute programs, right? They store everything on the hard drive, they throw it in memory in these 3 different segments, and then the processor is going to go through the code and run things in the appropriate order, reading and writing data as needed, and advancing the execution. We learned how the programs are stored and executed in memory. We learned how memory corruption can be exploited for fun and profit. That's just a throwback to one of the initial papers. So how we can actually take one of the bugs that would typically just crash the program, and this is, you know, anytime you get frustrated and throw your arms up like, oh my God, the program just crashed. If you are a hacker, your eyes light up. You're like, whoa, wonder how that happened, right? And you start digging into like, maybe there's an exploitable bug here. We deployed some memory corruption defenses, so went over some of the actually state of the art, but you know, simple, the ones that have actually been deployed on how you can defend these things, and advanced binary exploitation techniques. So like ReturnOriented Program is still kind of the creme de la creme. There's different ways to corrupt data and, you know, different things that can happen, but this is, you know, what the most elite in the world are still doing, and you now know that after a 30-minute talk. So please, nobody get arrested or use this for bad. This is for education. So what's next, right? This is always my biggest question. So I think as a community, I'm only speaking for myself, but I thought we'd be farther along by now. I didn't think, you know, binary exploits would still be such a big deal. And you can thank John von Neumann for this. So brilliant guy, but he was the von Neumann architecture is the one that had code and data in the same memory space. So we're kind of just paying the price with designing our, you know, entire computing architecture in a way that is probably just going to be unsafe forever. So you can use safe languages, all these other little neat tricks in software. But personally, I think that you're using hardware to protect very sensitive information is kind of the future we're going towards. So, you know, the execute only, non-executable stack, actually, that took a hardware upgrade. They now have like trusted execution environments, secure elements. There's a lot of cool hardware security advances that have been happening. So sort of my vision is that we can secure at least the important stuff, just like your credentials, basic things for now. Programs are probably still going to be exploited. But the idea is if we design this well, that even if everything is exploited, the valuable information and valuable interactions are still protected. So this is my goal. This is sort of where I see the future going. This is why I got my PhD in embedded systems and not in software, because I think we really need to loop hardware in there. So I think that we're going to need some hardware enforced security mechanisms that are hard to subvert. And then at the bottom here, you can see that there's a link on GitHub if you wanted to try this yourself. So give me 1 second. I think, don't remember which terminal window I had that I wanted to show you, but I will. Is it this one? All right, 1 second. I have it full screened and it seems like my screen share is very confused by that. This one. Okay, so hopefully everyone is seeing the little program here. I have no way to verify this.
We can see it.
Okay, great. So this is like a simple binary program that is going to check the password, right? Welcome to the super secure program. This is the same program we've been talking about. It has password, it has input, takes the input from the user, and does a string compare. And the main function just checks the password. Win will print you win, lose will print you lose, and there's some fancy stuff to make it colored. So we compile this program. So here we are running it as a binary, right? Welcome to the super secure program. We try test, wrong password, right? We try the right password, which I think is secret. You win. You must be an elite hacker, right? But now, here's the interesting one. So my name is Chad Spensky. My name is, and somehow we get the win function, right? So let's make sure I'm not teasing. We try any other password, nothing works. But somehow I was able to get this thing to execute perfectly and win. So there is a intro to binary exploits and some code if you want to dig into it a little more and see why in the heck my name is so special.
Hey, Chad.
Yep.
We can't see the terminal being shared.
Can't see it?
We can see the screen that says create a buffer for our password, create a buffer for our input, etc. But we can't see you running the test.
Oh, okay. So let's run the test again. Sorry. So now do you see this one? See me typing?
That we can see.
Okay. All right. Well, sorry. So let's do this again. So we tried test. I was using tabs. I didn't realize that it didn't switch over. So test says wrong password. If we do the correct password, it works, right? We try some other random stuff. It doesn't work. But if we do this, somehow we win. So that, I think is an elegant thing that we just went over that source code together. It's quite simple. Yet somehow I can type in this special string and I get past the password check, right? So this is binary exploitation at its finest. And at this point, I can put the link up there if folks want, and I'll answer any questions just in case you wanted to.
All right, so now we'll field some questions Chad's way. So make sure to put any and all questions that you have in the Q&A function, which should be at the bottom of your screen. Yeah, we'll just go through it. So first question, are there any playgrounds where you can learn to do this in a controlled environment and or any other recommended resources for how to learn?
Yeah, there's a bunch. So the best control environment is just your own computer. You're not going to break it, especially doing this kind of stuff. You'll just break the program. There's a bunch of like online resources. So Capture the Flags is where I learned most of this through. There's one book I really like by John Erickson called The Art of Exploitation. That one's really good. But if you go online, there's like ponables.kr. You can kind of Google just like capture the flag practices, and there's a lot of really nice write-ups. So they'll have, the exact program you're supposed to exploit and sort of walk you through step by step how to write the exploit, what's happening, even sometimes pointing to what tools they use so you can get accustomed to the tooling. But there's a lot of great resources thanks to the Capture the Flag community. And if you want to compete in Capture the Flags, I would reach out to me and I would happily facilitate that and help you get involved with it.
All right. Next question, how is this knowledge useful besides, just trying it out and kind of playing with it? What's sort of the practical element there?
For me, I think the biggest thing is just understanding what's happening, right? So if you're on the defensive end or you're just going about your daily life, not having this shroud in mystery of like, oh my God, what could have gone wrong, right? You actually understand that when you're writing source code, especially as a programmer, to just be extra careful, especially if you're writing low-level code, that these things can happen. And the way they happen is that you have things aligned in memory in a way or unchecked user input. So really as a programmer, I think it's important. As a non-programmer, someone just reading the news, I think it's nice to at least just have the insight into what a good hack is or something that's impressive, that like, wow, they actually sat down and reverse engineered this whole thing and were able to, do all this crazy tricks with the code. I think just an appreciation and to set your risk assessment appropriately, right? Some of these things are really, really, really hard. And I think the security industry kind of pushes them as like, oh, anyone can do it, right? it takes months of work sometimes.
Right on. Next question. Are there different paths for studying hardware vulnerabilities versus software vulnerabilities, and how can you learn about the former?
Very different paths. So I sort of specialize in hardware vulnerabilities. Software vulnerabilities, like I said, those would be all of the capture the flags and things like that. For hardware vulnerabilities, a good resource, that's actually, so there's a guy named Joe Grand that has a bunch of good content. If you Google him, like Grand, G-R-A-N-D, they teach classes as well that you can take. So if you have like a budget from your organization, I would highly recommend Joe Fitzpatrick, Joe Grand. Those guys are really good at doing hardware exploitation. I'll go a little bit into hardware exploitation next Monday. So if you want to learn more about it, I'm going over embedded systems and how to break them. But yeah, the avenue is very different. I mean, one of them, you kind of need to learn electrical engineering, and the other one, you need to learn sort of the software architecture. But yeah, I would say email me if you're really interested. My email should be up on the screen, and I'm happy to point you to resources.
All right, next question. When websites say there's a max character limit on passwords, is that related to exploits?
Yes, it very likely is related to exploits. It also just saves their database. You don't want to put, somebody has a 3 terabyte password or something silly like that. But so there's these buffer overflow exploits, and there's also what are called SQL injection attacks, where if the data going into the database is not sanitized properly, you can do sort of the same thing. It's with commands, not binaries, like so you won't be writing code. But you could put your password, there's like a funny XKCD on it, where they do like dash dash semicolon or semicolon dash dash and then drop tables, and it ends up deleting all of the student records at a school, and they're like, oh my God, did you really name your son this? So yeah, it is very likely for exploits.
Next question. Could you show us an example of rewriting code with your tiny program?
Right, so where the vulnerability was and how to fix it. Yeah, so Apple, I think if I click this one, let's see. Do you see the correct terminal up again? It says binary exploitation.
We're still seeing the slides.
Okay. It doesn't like it when it's full screen. Give me 1 second and then I'll share that. And I will show you exactly what went wrong and how to fix it. It's literally like 1 line. So that's a great question. So this one, you should see the terminal now. So we're going to look in here. So the issue that we have is that this input number can be bigger than this password. So in memory, or sorry, the input that we read can be bigger than the buffer. So we allocated 20 bytes, but then when we do the read, we're actually reading 1024 bytes. So in fgets, this is where it's going to put it. It's going to put an input. This is the maximum it's allowed, and this is where it's getting it from. So I did this intentionally to make it vulnerable, but if you did that, it's now fixed. That's pretty much the only change you would need to make. I also hard coded this down here, but this is the vulnerability. So that will save you from a lot of trouble. It's mainly checking length. That's like the biggest issue. And the reason this works, that this attack works, is that in C, a string is terminated by a 0. So a character that's all zeros, literally the number 0. So it will just keep reading until it sees a 0. Whereas if you did this, I'd say correctly, what you would do is you would encode the length first, and then, so you'd say 5 bytes are coming, here's the 5 bytes. And then we could easily have checked it and say, no, this is more than 20.
Right. Thanks for that little demo.
Yeah.
Next question. What's the coolest exploit that you've heard about but haven't yet spoken on?
Oh, the coolest exploit I've heard about that haven't spoken on. I don't know. I mean, I'm a hardware hacker kind of at heart, so I think those ones are super interesting. Yeah, I don't know. So there's one guy that went all the way through the smartphones. I forget, he had a really cool name for it. He works at Google, Project Zero. But they like started from exploiting the Wi-Fi controller on the phone, and then from that exploited the application processor, and then exploited the trusted execution environment, and went like all the way down the chain to take over every single aspect of the phone. And he did this over like a year and like kept blog posts as he was doing it. That I think was the coolest exploit ever. It was so much work and it chained together so many different layers. Like he just kept cracking one layer at a time. So I think that was probably the neatest. I wish I could remember his name off the top of my head right now, but it is eluding me.
Now more of a career development oriented question. Where specifically can someone get started if they're interested in becoming a cybersecurity professional, helping organizations find and prevent vulnerabilities and or tracking down people who've exploited those vulnerabilities? And they're curious about some specific places where to get started if you have zero background in any sort of technical realm.
Yeah, so this one's tough, right? Like we read all the time that, oh my God, we need more cybersecurity professionals, but there aren't many classes. So I don't think there's any high school classes, even at the university level, there really aren't much on how to get into this. So it ends up with people like me that are all self-taught and have kind of shady backgrounds. I think capture the flags is something I wish I had when I was a kid. I would really suggest getting into capture the flags. They'll teach you sort of everything that like attackers are doing. They tend to be pretty cutting edge and they hold them at all different skill levels. So when I was at UCSB, we compete at the most elite levels. We travel the world. We compete in DEF CON, which is like the Olympics of hacking. So, you know, to eventually get to that point is I think laudable, but yeah, I would highly recommend capture the flags because it's one of those things where hands-on is a must, which is why I put the code in my slide, just to kind of play with and actually see an exploit and open up a debugger and see how it's corrupting memory. You can't read about this in books. And even the book I recommended, it comes with a CD where you can go through and actually hack all of these things. So yeah, I don't know, an internship probably helps at like a security company, but even then it's tough to get if you don't have the skills. So we're very much in a chicken and the egg problem. I think in the future we'll see more classes about this stuff, or hopefully not. Maybe we just fix it, but I'm not that optimistic, unfortunately.
All right. So if there are any other questions at this point, make sure that you send them through the Q&A now. And otherwise, Chad, any concluding thoughts on this topic before we wrap up?
Not really. I mean, I hope this was insightful because I hope it made, you know, hacking a little less mysterious, that it's just, you know, you're overwriting things in memory, and when you overwrite really valuable things like, you know, sensitive data or a sensitive pointer in memory that's going to tell it what to execute, you can do, you know, bad things or really cool things depending on which way you look at it. But yeah, the whole intent of this was just kind of to show everybody, hopefully, an overview of what, you know, elite hacking looks like, this whole world of binaries and, you know, what goes on at the really low levels.
All right, and one final question I see coming in, favorite code editing tool?
I use a different editor for almost everything I do. So Vim is what I was using today in the terminal if I have to do something quick and dirty. I use PyCharm for Python, CLion for C, C++, VS Code for like front-end web development. I'm definitely a big proponent of IDEs, though. I have a lot of friends that think, you know, you're a noob if you don't use Emacs or Vim, but you move way faster in an IDE. I would highly recommend getting a good one. The IntelliJ makes all of the PyCharm like IDEs, and then VS Code, I think, are kind of the two top ones right now.
Right. So with that, we'll wrap up a little bit early. But thank you so much, everyone, for coming today. If you enjoyed hearing from Chad for today's session, make sure to check out the event calendar that was, again, just sent out through the chat. So Chad has this month joined us for a variety of great hacking-related events. And next Monday is our last one. It's going to be all about embedded systems, like Chad mentioned. So Monday, October 26th, noon to 1. Don't miss it. You can register through that link that was just sent out. And also, Chad will be giving another talk this Thursday, October 22nd at 4 p.m. And we'll be hearing all about the state of authentication, which is bound to be a fantastic session. So all of the registration links and details for all of those events and any other events that are happening for National Cybersecurity Awareness Month can be found in that link that was sent out. And you can also follow at UCSB InfoSec on Facebook, Twitter, LinkedIn, or Instagram for the most up-to-date information about all the events that UCSB is hosting this month. So thank you again for joining us, and we'll see you at the next session. Have a good one, everyone.
Sounds good. And I encourage you to reach out if you're interested in those things, and I will send you any pointers.